All right, everybody, welcome to lecture 17, video number 1. This is a thermodynamics review. Let's get right into it. So, we've learned about solar and wind technology so far. And these technologies specifically convert high quality energy into a different form of high quality energy. So with solar, we convert very high temperature heat from the sun at 5800 Kelvin into electricity. Oof, that's a lightning bolt. And then with wind turbines, we turn wind into electricity. Wind is kinetic energy. The sun is very high temperature thermal energy. Very high temperature, which means it's high quality. Okay? And that's great, but now we need to focus on a different approach, specifically converting low quality energy, specifically low temperature thermal energy, into high quality energy, specifically electricity. Oops. Okay, so you see how this is different than what we've done before, right? Up till now, we've only looked at high quality to high quality. Now we're going to go low quality, because we're going from low temperature thermal energy into high quality energy, or electricity. Okay, so some of the applicable technologies that we're looking at today that utilize what we're talking about now are geothermal, both for power generation, so electricity generation, and for a heat pump to heat your home or even to cool your home. Also nuclear, we're taking, it's sure nuclear doesn't generate a low temperature, but it's not as hot as the sun, right? So it's still a relatively low quality energy, converting it upwards into electricity. And also biomass, or burning essentially plants in order to generate electricity. That's a very low temperature usage usually. Okay. And so in order to do all of these things, we are going to talk about a very basic idea, a very basic technology that came about several hundred years ago and we now cannot live without: the heat engine. Let's talk about the heat engine. Okay, so for most heat engines, we kind of draw them schematically like this. So we just draw a circle. This is our heat engine, this circle. Okay, and what a heat engine does is it's a device, and its only job is to turn heat into work. When we say work, we mean something like mechanical work. So take heat, just the movement of energy, the movement of thermal energy, and turn it into mechanical work. You're very familiar with heat engines because you use lots of them every day. When you get into a car and start the engine, lo and behold, you are turning combusted gas, right? You're combusting gasoline, turning it into hot air, and somehow that hot air magically turns into rotating tires. That is a heat engine. Okay, so here's our heat engine. And what we're going to do is we're going to add heat to it, QH, from a high temperature reservoir. That's TH. And then we're going to reject some of that heat, QL, to a low temperature reservoir. Okay, so this high temperature reservoir is our energy source. This is where we're getting the energy from. And then some of that energy, our heat engine will turn into work. So some heat is converted to work. However, one property of heat engines is that some heat that we originally took from this TH reservoir is wasted. In fact, it must be wasted. That's just the laws of thermodynamics. That is the second law, right? If we're going to convert from low quality to high quality, we have to pay the price. Some of that low quality energy must not be converted to high quality energy. Okay. Okay, so a heat engine, oops. So far I've just drawn it as a circle. That's pretty ambiguous. So what is it really? Well, a heat engine consists of components, all right? And these components complete a series of processes. On what we usually call a working fluid. And this creates a cycle. The best way to explain this is to give you an example. So let's do an example being your car engine, because I think enough people are familiar with that to jive with this, right? So your car engine, we've got your piston, your cylinder, and we've got a piston inside that cylinder. So remember, we have a series of processes. So let's look at process number one. We will call it intake. So in the intake process, your intake valve opens and fresh, cold air is drawn into your cylinder. And it's drawn in because this piston is being pulled down. It's doing work and pulling this fluid into your cylinder. Okay, once it's pulled it in, then we do another process, compression. So now both valves at the top of your cylinder are closed, and now your piston is pushed up by the other pistons that are expanding. We'll see that in a second, but this is being pushed up. And as it's being pushed up, it's compressing the air. So the pressure and the temperature of the air will increase in this process. Then we have the third step, ignition. So little did you know that some gasoline has been squirted into the air. And just when you've compressed it all the way to the top and the air is already so hot and so pressurized, you do a little spark and you ignite all of the gasoline. And what that does is it adds energy. So we've just added energy, right? In the form of chemical energy, which then turned into thermal energy. And now this air has a much higher pressure and a much higher temperature, and it pushes down on this piston. And so you see we've turned thermal energy as heat into mechanical energy. We've pushed downward on this piston. Okay, however, we can only expand our piston so far. It can only go down here to the very bottom. But by the time we get there, we've added so much energy that our air will still be hot and we'll still have some pressure, right? But there's nothing we can do with that. We could try to expand it forever, but that would take so long. So instead, we're going to exhaust the air that is left over by once again pushing our piston up, and now the remaining somewhat hot, somewhat pressurized gases are pushed out. And so that is our waste heat that we talked about earlier. Okay, so this right here is a series of processes completed by components, and it creates a cycle, right? As soon as you finish exhaust and your piston's up at the top, you go all the way back to step number one, and you do 1, 2, 3, 4, 1, 2, 3, 4. like 7,000 times a minute, and you've got a vehicle. Okay, so before we wrap up with heat engines, all heat engines, and there's a lot of them, right? So there's your car engine, there's a coal power plant, even natural heatings exist, like the water cycle. The water cycle, right? Energy is added to the water as sunlight, which causes the water to rise. It does work on the water. The water then moves and then cools and then runs back to the ocean, and you have a cycle. That's a heat engine. Okay, so the performance of all heat engines is compared against the ultimate theoretical heat engine, the Carnot heat engine. We're not going to talk about exactly what processes the Carnot heat engine consists of, but what matters is the Carnot heat engine is entirely theoretical. We've never actually built one because it's impossible, and it is the most efficient heat engine operating between two temperatures, TH and TL. Remember, our heat engines operate between a source and a sink. Well, for a given TH and TL, a Carnot heat engine has the most efficient performance of all heat engines for those given temperatures. However, it would take a long time in order to do even a single cycle of the Carnot heat engine, which is one reason why we don't build them. You would get almost no power out. But the reason we talk about them is it's a good kind of test to see how good your real engine is by comparing it to this theoretical best engine. So I'm just going to draw real quick a Carnot heat engine. So here's a Carnot heat engine. Okay. We can draw a control volume around it. We've got QH, QL, and the total amount of work we actually get out of our system. So we can quantify the efficiency of our Carnot heat engine. Efficiency, remember, is always what you want. So in this case, what do we want out of a heat engine? We want work. That's what you want out of your vehicle. You don't want hot air. You want moving tires. So you want work divided by what you have to put in. So what you want over what you put in. In this case, we have to put in QH. So that is the efficiency of any engine. For a Carnot heat engine, we can also write that. I'm obviously not going to go through this proof like this, just as a function of our two temperature extremes. So if we know TL and TH, we can find the best possible efficiency we can get. And if we know QH, we could then find the total best amount of work we could get out there. Okay, so that's a brief review of heat engines. Next, we're going to go into a few cycles. The first one is the Rankine cycle, which is very applicable to things like power plants.